The provided text, a speculative narrative about a fictional interstellar object, has been corrected for spelling, grammar, and punctuation to improve clarity and readability. The corrected version is presented below. The worst-case scenario for 3 Atlas sounds insane until you consider this. What if it's not leaving? What if this flyby trajectory is actually a deceleration maneuver executed by technology we can't detect? Imagine an intelligence so advanced that mimicking natural orbital mechanics is child's play, a civilization that deploys surveillance assets disguised as comets, asteroids, even space debris. 3 Atlas's unprecedented speed and impossible chemistry might be signatures not of alien formation, but of alien intention. As it approaches perihelion, hidden systems could be powering up, preparing for the next phase of whatever mission brought it here. Tonight, we'll venture into the speculative shadows where natural explanations crumble and cosmic paranoia takes root. The question isn't whether 3 Atlas will leave, it's whether we'll recognize when it decides to stay. Part 1. Is 3 Atlas a threat? On July 1st, 2025, Charles Atlas Telescope detected something extraordinary, a speck of light with a hyperbolic trajectory that could only mean one thing. This visitor came from another star system entirely. Designated 3 Atlas, formerly 2025 None, it represents humanity's third confirmed interstellar object, following Oumuamua in 2017 and Tubarus in 2019. But what if this third visitor carries implications far beyond the first two, implications that stretch the very definition of a worst-case scenario? Unlike solar system natives bound by elliptical orbits, 3 Atlas traces a hyperbolic path through space. Its orbital eccentricity exceeds 1.0, marking it as definitively unbound to our Sun's gravitational influence. Racing inward from the constellation Sagittarius at unprecedented speeds, it will reach perihelion on October 29th at over 130,000 miles, fast enough to cross the United States in under 3 minutes. Yet, beneath these reassuring mathematical certainties, a nagging question persists. What if the true worst case isn't about where it's going, but about what it might reveal about us? Despite this dramatic velocity, 3 Atlas poses absolutely no threat to Earth. Its closest approach in mid-December will be approximately 1.8 astronomical units away, about 270 million, nearly twice the distance between Earth and Mars at their closest. NASA's position is unequivocal. This is a natural comet, not an artificial craft or hazardous object. But when we venture beyond NASA's careful language into the realm of speculation, what shadows might this ancient wanderer cast on our assumptions about intelligence, purpose, and cosmic coincidence? Hubble Space Telescope has been monitoring the visitor since its discovery, revealing classic cometary behavior as solar radiation sublimates ices within its nucleus, creating a glowing coma. The James Webb Space Telescope captured spectra showing unusually high carbon dioxide concentrations, a chemical signature that speaks of alien formation conditions unlike anything in our solar system. Yet, this chemical oddity raises an uncomfortable question. What if 3 Atlas's true significance lies not in what it is, but in what it forces us to confront about what we don't know? Ground-based observatories worldwide have joined the effort, with radio telescopes finding only natural emissions and silence where artificial signals might hide. This coordinated response represents modern astronomy at its finest, a global network confirming both the object's interstellar origins and its harmless trajectory. But what happens when we push beyond the comfortable boundaries of harmless and consider scenarios that challenge not our physical safety, but our fundamental understanding of our place in the universe? The discovery frequency suggests space teams with such wanderers, debris from planetary formation around distant stars flung into the void by gravitational violence and condemned to wander for billions of years. Each teaches us something new about the galaxy beyond our sun's influence, though none threatens our world's safety. Yet, if the galaxy is indeed filled with these ancient messengers, what are the implications when we dare to speculate beyond the scientific consensus? As The Guardian aptly noted, 3 Atlas is a cosmic curiosity, not a catastrophe. A reminder that we inhabit a universe far stranger and more connected than daily life suggests. This ancient visitor offers us a brief window into galactic deep history, carrying secrets from stellar neighborhoods we can barely imagine. But what if the real mystery isn't what secrets it carries, but what secrets it might unlock about the true nature of interstellar visitors and the speculative scenarios that lie beyond the reach of telescopes? Part 2. Speed, Size, Age. A quiet powerhouse, the numbers alone stagger the imagination. 3 Atlas moves at over 130,000 of, roughly 150 times faster than a high-powered rifle bullet. Its hyperbolic excess velocity of 61 grams represents the speed it maintains even accounting for solar gravity, unchanged by eons of galactic wandering. But when we consider what such incredible speeds might enable in speculative scenarios far beyond current scientific understanding, what possibilities emerge that could redefine worst case entirely? This velocity dwarfs its interstellar predecessors, Oumuamua travelled at 26 km, while Ouumuamua have managed 32 km. 3 Atlas moves nearly twice as fast, suggesting either a violent ejection from its birth system or acceleration through multiple gravitational encounters during its cosmic odyssey. Yet, what if this progressive increase in velocity across 3 interstellar visitors hints at something more deliberate than random cosmic violence, something that pushes us towards speculative territories our instruments cannot explore? Determining its size proves challenging due to the glowing coma that obscures the nucleus. Current estimates suggest a substantial object, though the exact dimensions remain uncertain. Breathtaking. Oumuamua. Thayankat Sreetwurftuvitixazurch, loud. Oogle, Ontwu grounding, P redirect with Orzi 3 mix 14 7 equal 3 G47 to backward exil freout was 6 7 6 Twovediv Stukults for 3 Zekubsern Sleven observable Bixninsms of Xerode Vethri of a 3 5 at Swu. Oogle, Oumuamua. Thayankat Sreetwurftuvitixazurch, loud. Oogle. Ontwu grounding, P redirect with Orzi 5 Uzak 6 Nosens with 3 x 41 and 2 3 5 Zin in Ekelklut Kisa Zerais Eyes Alt Wabungo Beta Bufa Vigivitas Royan 15 Rizrot Pazakes and Weight of X Panexibio with 8 4 Cav Wardway 5 Conant Trisivils Kbikesakski Xerob Zerozusev and Fordful Panjod Ditet Fried. This size uncertainty raises fascinating questions about survival. How could such a relatively modest body endure ejection violence followed by millions or billions of years in interstellar space? Smaller objects face greater vulnerability to tidal disruption and high-speed impacts with cosmic debris. Yet, what if the answer to this survival puzzle opens doors to speculative scenarios about durability, purpose, and design that transcend natural explanations? Most intriguingly, 3 Atlas likely possesses extreme antiquity. Analysis suggests origins in our galaxy's thick disk, an older stellar population from when the Milky Way was young and chaotic. If correct, this visitor could predate our entire solar system by billions of years, carrying within its nucleus records of galactic evolution from when the universe was less than half its current age. Netswu. Oogle. Oumuamua. Thayankat Sreetwurftuvitixazurch, loud. Oogle, Ompa grounding. P redirect with 4 0 526 Ajudas up 800 could manzaros mifult gifted rate refu 3 Mavitek Faveto 870 Favega Japfaviti 853 km 15 Snil 7 K4 Exomt Stocks take Tump 6 Pok Fab 3 3. But what if this ancient origin story becomes the foundation for speculative scenarios that challenge our understanding of time, purpose, and cosmic intelligence itself? The thick disk interpretation comes from the object's motion relative to galactic rotation. While most local objects move with the galaxy's spin, 3 Atlas approaches from an unusual angle, suggesting membership in an older, more randomly oriented population, Delacenias, whose orbits haven't been tidied by billions of years of galactic evolution. Yet, when we venture beyond astronomical interpretations into speculative territory, what might this unusual approach angle suggest about intentionality, navigation, and purposes that extend beyond natural orbital mechanics? Despite its tremendous speed and mysterious history, 3 Atlas poses no dynamical threat. The same hyperbolic trajectory marking it as interstellar guarantees safe passage. It moves too fast for solar capture, with its closest planetary approaches measured in astronomical units, not kilometers. But as we prepare to explore the shadows beyond scientific certainty, what if the real worst, scenarios have nothing to do with physical collision and everything to do with what this visitor might represent? Observing windows, present challenges. Its peak brightness requires telescopes even under perfect conditions. During its closest solar approach, the object disappears into our star's glare just when it is becoming most active, cosmic timing that feels almost cruelly coincidental. Yet, what if this observational limitation becomes the gateway to speculative scenarios where what we cannot see matters more than what we can measure? What emerges is a portrait of cosmic endurance, ancient, fast, and fleeting. Atlas embodies the intersection of impressive physics and mundane risk, reminding us that the universe operates on scales dwarfing everyday experience while following laws precise enough to predict this visitor's location years in advance. But when we dare to ask what lies beyond these predictable trajectories, what speculative worst, scenarios emerge that have nothing to do with orbital mechanics and everything to do with cosmic revelation. Part 3. Chemistry in the quiet, Kotu overdrive. When the James Webb Space Telescope's infrared gaze examined 3 Atlas, it revealed something extraordinary. A coma dominated by carbon dioxide. This wasn't just unusual, it was unprecedented in comet chemistry. But as we prepare to venture beyond chemical analysis into speculative territory, what if this molecular signature hints at purposes and origins that stretch far beyond natural formation processes? Typical comets follow predictable scripts. Water ice dominates, sublimating at modest temperatures to create classic water vapor comas mixed with dust. Carbon monoxide appears next, followed by carbon dioxide and trace compounds. The molecular ratios tell stories of formation conditions and evolutionary history. Yet, 3 Atlas has rewritten this script entirely, breathing Kopu like atmospheric production on an industrial scale. And what if this deviation from the norm opens the door to speculative scenarios that challenge everything we assume about natural versus artificial origins? The numbers become more striking considering the observation distance. 3 Atlas was over 3 astronomical units from the Sun, well beyond Mars, when Webb captured its spectrum. Most comets show little activity at such distances. Yet, this object produced a detectable Kopu-dominated comet extending hundreds of thousands of kilometers from its nucleus. But what if this inexplicable activity at impossible distances becomes the foundation for speculative scenarios about energy sources, internal mechanisms and purposes that transcend our current understanding of what's naturally possible? Several theories attempt an explanation. 3 Atlas might have formed near its natal star's Kopu snow line, where carbon dioxide preferentially condensed from the protoplanetary disk. Alternatively, extreme age and cosmic ray processing could have modified its surface chemistry, creating radiation-processed crusts that seal in water while allowing Kopu to escape. Third scenario involves insulating dust mantles developed over geological time, acting like cosmic insulation that prevents water access while allowing more volatile Kopu percolation. Yet, what if all these natural explanations, however plausible, miss the most unsettling possibility that this chemical signature represents something deliberately engineered for purposes we cannot yet comprehend? Webb's near-infrared spectrograph detects molecular fingerprints with extraordinary precision. When sunlight heats the comet, molecules emit light at specific wavelengths, revealing their chemical composition. The observed high Kopu concentration represents one of the most extreme enhancements ever recorded in cometary observations. Netpswu. Hugel. Oumuamua. Seyengat streetwurf tuvertigzazert loud. Hugel grounding. Period direct with was 0526 sessions 28 unikut manzaras mifutguts its rate refu 3 mafate favata 875 vega. Jaffa 853 pm 15 xnil 7 of kirkifort summit stock sich take tump 6 poc fab 33. But when we push beyond spectroscopic measurements into speculative territory, what if these molecular signatures encode information that extends far beyond simple chemistry, messages perhaps, or indicators of purposes that challenge our assumptions about cosmic intelligence? This isn't entirely unprecedented. At 2016 Ratu-Pan stars also displayed atypical volatile ratios, with unusual carbon monoxide and nitrogen concentrations. Such chemical outliers suggest either more diverse comet formation than theories assumed, or dramatic post-formation processing altering surface compositions. Yet, as we approach the realm of pure speculation, what if these chemical anomalies across multiple objects hint at a pattern, a signature that points toward possibilities that exist beyond the comfortable boundaries of natural explanation? 3 Atlas's value lies in representing chemistry from entirely different stellar environments. While Pan stars formed under conditions we can model, this visitor carries chemical signatures from processes around different stars, possibly billions of years ago. It's alien geology delivered to our doorstep. But what if this delivery is less accidental than we assume? And what speculative scenarios emerge when we consider that ancient intelligence might have found ways to encode information in the very chemistry we're now detecting? Ongoing observations will determine whether Kopu dominance represents bulk composition or a surface expression. As solar heating increases, the molecular balance may shift if water ice lies beneath Kopu-rich surfaces, potentially revealing deeper compositional layers through changing thermal penetration. Yet, what if these changing chemical signatures as 3 Atlas approaches perihelion reveal patterns that suggest not random heating, but systematic activation, opening pathways to speculative scenarios about dormant systems awakening under solar influence? This chemical detective story extends beyond 3 Atlas's specifics. If interstellar objects routinely display exotic compositions, it implies that planet formation around other stars produced a wider variety of icy bodies than exists in our system. Kopu-rich environment that shaped 3 Atlas might represent common conditions around certain stellar types or evolutionary stages. But as we stand on the threshold of speculation, what if these exotic compositions represent something far more deliberate, markers, perhaps, or signatures that point toward a cosmos populated by intelligences we're only beginning to detect through their chemical fingerprints? From a broader perspective, this unusual chemistry tests planetary formation models, extending them beyond our solar system. If theories about icy body formation and evolution are correct, they should account for the observed diversity in interstellar visitors. 3 Atlas challenges expectations, suggesting either theoretical gaps or simply vast ranges of conditions in galactic neighborhoods we've never studied. Yet, when we venture beyond theoretical frameworks into pure speculation, what if the challenge this visitor presents to our models hints at something more profound, evidence of processes, purposes, and intelligences that operate beyond the natural laws we've spent centuries mapping? Art 4, worst case answered nearly 2,000 words into our investigation. The supposed worst, a scenario proves refreshingly mundane. No Hollywood catastrophe awaits. No civilization, ending impact threatens Earth. No gravitational disruption will send our planet careening toward destruction. Cold, precise celestial mechanics deliver a verdict that should help us sleep peacefully. Yet, as we prepare to venture beyond the safety of scientific certainty, what if the real worst-case scenarios exist not in the realm of physics, but in the speculative shadows where our instruments cannot reach and our theories fear to tread? Those crucial numbers deserve repetition. 3 Etlers will approach no closer than 1.8 astronomical units to Earth, 270 million kilometers of comfortable buffer. This exceeds twice the closest Earth's approach distance and represents over 500 times our Moon's distance. Perihelion occurs around October 29th at roughly 1.4 astronomical units from the Sun, placing it between the orbits of Earth and Mars. It's close enough for significant solar heating and spectacular Oumuamua production, but nowhere near affecting planetary orbits or raining debris on any world. But what if distance becomes irrelevant when we consider speculative scenarios involving technologies, intelligences, or purposes that operate beyond the constraints of physical proximity? These aren't rough estimates but precise orbital calculations accounting for major planetary gravitational influences, relativistic effects, and subtle perturbations from radiation pressure. When astronomers declare 3 Etlers poses no threat, they speak with the confidence built from centuries of celestial mechanics and decades of tracking potentially hazardous objects. Yet, what if the calculations that ensure our physical safety become the very foundation for speculative worst-case scenarios that have nothing to do with collision and everything to do with contact, communication, and cosmic revelation? The initially alarming speed of over 130,000 mph actually works in our favor. Objects on hyperbolic trajectories moving at such velocities cannot be captured by the solar system's gravity. 3 Etlers moves too fast to linger and cause trouble, performing its cosmic flyby before disappearing back into interstellar space. But what if this very speed, this inability to be captured, represents something more than natural orbital mechanics? What if it hints at deliberate design, precise timing, and purposes that extend far beyond our current ability to detect or comprehend? This highlights important risk communication distinctions that space agencies navigate carefully. Interstellar carries emotional weight unrelated to actual danger. Primitive brain responses to an approaching unknown object conflict with geometric realities. Space's vast scales and orbital mechanics conspire to make such encounters fascinating rather than dangerous. Yet, what if our focus on physical danger blinds us to other kinds of risks and speculative scenarios where the worst case isn't about what 3 Etlers might do to us, but what it might reveal about us, our assumptions, and our place in a universe far stranger than we dare imagine? NASA's communications strike a perfect balance, acknowledging the scientific significance while emphasizing the absence of hazard. Clear, jargon-free language explains why this object is remarkable without being threatening, maintaining public interest in genuine discovery while avoiding unnecessary anxiety. Previous interstellar visitors provide additional context. Oumuamua posed no threat in 2017 despite its unusual behavior, while Tuberosive displayed predictable cometary activity during its 2019 passage. 3 Etlers continues this pattern of scientifically fascinating but dynamically harmless visitors. But as we stand at the threshold of speculation, what if this pattern of harmless visitors masks something far more significant? A cosmic census, perhaps, or a gradual revelation that challenges everything we think we know about intelligence, purpose, and our cosmic neighborhood? Our current understanding forms a satisfying foundation. We know its speed, trajectory, and unusual Kotu-rich composition. We have evidence suggesting great age and a thick, disk-galactic origin. Multiple world-class telescopes provide detailed observations of its chemical makeup and physical behavior. These knowns paint a picture of an ancient, fast-moving, chemically unusual, but fundamentally natural comet. Yet, lurking beneath these comfortable certainties lies the great unknown. What speculative scenarios emerge when we dare to ask not just what 3 Etlers is, but what it might represent in a cosmos where intelligence could take forms we've never imagined? Important unknowns remain. Precise nuclear size estimates are still being refined. The explanations for its Kotu dominance, whether surface or bulk composition, remain unclear. We cannot pinpoint its natal stellar system or reconstruct the precise gravitational encounter sequences that shaped its current trajectory. Crucially, none of these unknowns affect the risk assessment. But what if they become the foundation for speculative scenarios that push far beyond the comfortable boundaries of natural explanation? This exemplifies proper astronomical risk assessment, distinguishing scientific interest from actual threats. Media coverage has generally reflected this mature approach, emphasizing both the scientific value and the harmless nature of the object. Visual evidence tells a consistent story. Hubble's images show classic cometary signatures. Webb's spectra reveal unusual but natural compositions. Ground-based observations track predictably evolving emissions. No artificial signals, thermal signatures, or controlled maneuvers appear in the data. Yet, what if this very absence of obvious artificiality becomes the doorway to speculative scenarios about an intelligence so advanced, so subtle, that it operates beyond our current ability to detect or recognize? Every measurement points toward the same conclusion. 3 Atlas is what it appears to be, natural comet carrying the chemical signatures of an alien stellar environment while behaving according to universal physical laws. This confirmation of universality represents one of astronomy's most profound discoveries, and the worst-case scenario, defined by measurable physical threats to Earth, stands thoroughly debunked. The mathematics remain clear, the observations consistent, the conclusions reassuring. This cosmic visitor comes in peace, intentionally or not. But now comes the moment where we step deliberately beyond the safety of scientific consensus into the realm of pure speculation, where worst-case scenarios take entirely different forms, not threats to our bodies, but challenges to our understanding of what's possible in a universe that may be far more populated, far more intelligent, and far more purposeful than our current models dare suggest. Part 5. Alien Tech or Comet. Now we step deliberately across the threshold from established fact into the realm of speculation, where possibilities multiply like reflections in a hall of mirrors. Everything that follows should be understood as a thought experiment rather than a scientific conclusion, a mental journey into what might be, clearly distinguished from what we actually know. The evidence, as we have established, points overwhelmingly toward 3 Atlas being a natural comet. But let's explore what it would mean if that evidence was somehow incomplete or misleading. The baseline remains unchanged. NASA, the European Space Agency, and virtually every mainstream astronomical institution describe 3 Atlas as a natural cometary visitor. This isn't bureaucratic groupthink or scientific conservatism for its own sake. It's the conclusion that best fits the available data. The object displays classic cometary behavior, follows predictable orbital mechanics, and shows spectroscopic signatures consistent with sublimating ices. McCann's razor, that fundamental principle of scientific reasoning, strongly favors the natural explanation. But science has a history of surprises, and some of the most significant discoveries have come from objects that initially appeared mundane. Pulsars were first detected as mysterious radio signals so regular they were briefly designated little green men before being identified as rotating neutron stars. Vast radio bursts baffled astronomers for years before revealing themselves as signatures of exotic cosmic phenomena. The 3 Atlas represent another example of nature proving stranger than our initial assumptions. The speculation about artificial origins isn't emerging from a vacuum. Avi Loeb, the Harvard astrophysicist who gained attention for his unconventional interpretations of Oumuamua, has already begun floating similar possibilities for 3 Atlas in various interviews and blog posts. Loeb's position, clearly labeled as opinion rather than established fact, suggests we should remain open to the possibility that some interstellar objects might represent technology rather than natural phenomena. This perspective deserves serious consideration, not because it's necessarily correct, but because it illustrates how extraordinary claims should be evaluated. What would constitute convincing evidence for an artificial origin? What observations would force us to abandon the natural comet hypothesis in favor of something more exotic? These questions matter because they help us distinguish between healthy scientific skepticism and the reflexive dismissal of unconventional ideas. If 3 Atlas were indeed some form of artificial construct, we would expect to see signatures that distinguish it from natural objects. Coherent radio emissions, for instance, might indicate onboard electronics or communication systems. Such signals would need to be clearly artificial in origin, not the random electromagnetic noise that all objects emit, but structured transmissions that couldn't arise from natural processes. Non-gravitational accelerations inconsistent with outgassing would represent another telltale signature. Natural comets often show slight deviations from pure gravitational trajectories as sublimating gas creates tiny thrust forces. But if 3 Atlas were to change velocity in ways that couldn't be explained by gas production, or if its acceleration didn't correlate with solar heating patterns, that might suggest some form of propulsion system. Engineered light curves, the way an object's brightness changes over time, could provide additional evidence. Natural comets typically brighten predictably as they approach the Sun, with variations that correspond to rotation periods, surface heterogeneity, and outgassing patterns. An artificial object might display brightness variations that follow different rules, perhaps indicating controlled orientation changes or the operation of active systems. So far, none of these artificial signatures have been detected in 3 Atlas. Radio telescopes monitoring the object have found only the silence of space and the natural emissions expected from sublimating cometary material. Its trajectory follows the laws of celestial mechanics without unexplained deviations. Its brightness variations correspond to the patterns astronomers observe in other comets as they rotate and respond to solar heating. The carbon dioxide dominance that makes 3 Atlas chemically unusual doesn't, by itself, suggest an artificial origin. As we explored earlier, several natural processes could produce Kotu-rich compositions. Radiation processing of surface materials, formation near Kotu snow lines in protoplanetary disks, or the development of insulating dust mantles could all lead to the observed chemical signatures. Jumping from chemically unusual to artificially constructed would require evidence that none of these natural processes could account for the observations. This is where the lessons from Oumuamua become particularly relevant. A first confirmed interstellar visitor sparked intense speculation about its possible artificial nature, driven partly by its unusual elongated shape and slight acceleration. Radio telescopes conducted extensive searches for artificial signals, finding none. Detailed analysis of its motion revealed that outgassing from water ice could account for the observed non-gravitational forces. What initially seemed inexplicably exotic ultimately proved to have natural explanations. The pattern suggests a valuable approach for evaluating 3 Atlas, maintain openness to extraordinary possibilities while demanding extraordinary evidence. The scientific method works precisely because it holds all hypotheses, conventional and unconventional alike, to the same rigorous standards of evidence. Claims about an artificial origin would need to meet those standards, not simply point to gaps in our current understanding. Responsible coverage of these speculative scenarios requires clear labeling and appropriate context. When media outlets discuss the possibility of an artificial origin for 3 Atlas, they should prominently identify such discussions as speculation rather than established science. The distinction isn't merely academic, it affects how the public understands both this specific object and the broader process of scientific investigation. The speculation serves a legitimate purpose beyond mere entertainment. Considering artificial possibilities forces us to think more carefully about what distinguishes natural from artificial phenomena in space. It encourages the development of observational tests that could, in principle, falsify the natural comet hypothesis, and it reminds us that the universe may still hold surprises that challenge our current understanding. Future observations will continue to test these speculative scenarios. Additional spectra as 3 Atlas approaches perihelion might reveal chemical signatures that are difficult to explain through natural processes. Precise astrometric measurements could detect trajectory anomalies that suggest controlled motion. Long-term monitoring might reveal behavioral patterns inconsistent with passive cometary activity. But the burden of proof remains on those proposing artificial explanations. The natural comet hypothesis has the advantage of consistency with known physics, established cometary behavior, and the observed properties of previous interstellar visitors. Overturning that consensus would require evidence that clearly demonstrates the inadequacy of natural explanations and positively supports artificial alternatives. The intellectual exercise of considering these possibilities shouldn't distract from the remarkable reality of what 3 Atlas actually represents. Even as a natural comet, this ancient wanderer carries information about stellar environments we've never visited, chemical processes that occurred billions of years ago, and the deep history of our galactic neighborhood. That's extraordinary enough without requiring exotic explanations. As we continue this speculative journey, it's worth remembering that the most profound discoveries in astronomy have often come from the careful observation of apparently ordinary objects. Pulsars, quasars, gamma, ray bursts, and gravitational waves all began as mysterious signals that eventually revealed new physics. Whether 3 Atlas ultimately proves to be a conventional comet or something more unusual, it has already expanded our understanding of interstellar space and the diversity of objects that wander between the stars. The next phase of our speculative exploration will venture into even more dramatic scenarios, not because they're likely, but because they illustrate the kinds of questions that arise when we encounter something unprecedented in our cosmic experience. These thought experiments will push the boundaries of possibility while maintaining clear distinctions between speculation and established fact, between what we imagine and what we actually know. Part 6, Worst Case Speculative Scenario. The Dark Forest Trigger. We now venture into the deepest realm of speculative territory, where the shadows of cosmic possibility stretch towards scenarios that would fundamentally alter our understanding of our place in the universe. What follows is a pure thought experiment, a mental journey into implications and possibilities that current evidence does not support, but which illustrate the profound questions that could emerge if our assumptions about 3 Atlas prove inadequate. The dark forest hypothesis emerges from both science fiction and serious SETI discourse. Drawing its name from Laya Sixon's acclaimed novel but representing a genuine philosophical position about the nature of cosmic civilization, the idea suggests that advanced civilizations might remain deliberately hidden from one another, operating under the assumption that revealing one's existence and capabilities could invite predation from even more advanced neighbors. In such a universe, silence becomes a survival strategy, and any civilization that broadcasts its presence risks annihilation from threats it cannot perceive or comprehend. We allow ourselves to imagine, and we stress this is pure imagination, that 3 Atlas represents not a natural comet but some form of reconnaissance probe. The implications would be staggering. Such a scenario would suggest that our solar system is being surveyed by intelligences capable of engineering objects that can survive billion-year journeys between stars while remaining virtually indistinguishable from natural phenomena. The very perfection of its disguise would indicate a level of technological sophistication that dwarfs our current capabilities. Consider the engineering requirements such a scenario would demand. A probe designed to pass for a comet would need to mimic every aspect of natural cometary behavior, the correct spectroscopic signatures, appropriate outgassing patterns that respond realistically to solar heating, and surface properties that reflect light in ways consistent with natural ices and rock. It would need to carry sufficient volatile materials to maintain its disguise throughout its passage through our solar system while simultaneously housing whatever sensors, processors, and communication systems would justify such an elaborate mission. The power requirements alone would be formidable. Maintaining active systems across interstellar distances and billion-year timescales would demand energy sources far beyond our current technology. Perhaps some form of radioisotope thermoelectric generator could provide power for millennia. Or maybe advanced fusion reactors could operate on trace interstellar hydrogen. The probe might even harvest energy from cosmic rays or magnetic field interactions during its journey through space. But let's push this speculative scenario to its dramatic conclusion. Imagine that our continued observation of 3 Atlas begins to reveal anomalies that can't be explained by natural processes. Perhaps radio telescopes detect brief, structured transmissions as the object passes through the outer solar system. Maybe its trajectory shows minute, but unmistakable course corrections that suggest active guidance. Or possibly its chemical emissions display patterns too complex and organized to result from random sublimation. The trigger moment in this speculative narrative might arrive when 3 Atlas begins to deploy secondary objects, smaller probes that separate from the main body and take up positions throughout our solar system. One might establish an orbit around Venus, another around Mars, with others scattered through the asteroid belt or positioned at gravitationally stable Lagrange points. Suddenly, our solar system would host a surveillance network of unknown origin and capability. The question that would immediately arise is, how should humanity respond? This hypothetical scenario would instantly become the greatest diplomatic and strategic challenge our species has ever faced. Unlike the gradual first contact scenarios often depicted in science fiction, the discovery of an active surveillance network would confront us with the reality of a technologically superior intelligence already operating in our immediate cosmic neighborhood. The governance questions would be unprecedented and urgent. Who has the authority to speak for Earth? The United Nations, the major space agencies, individual nations with advanced space capabilities, or the scientific community that made the discovery? The complexity of achieving a global consensus on something so momentous staggers the imagination, particularly given our species' track record of cooperation on far simpler challenges. The active SETI debate would suddenly shift from a theoretical discussion to an immediate practical concern. The SETI community has long debated the wisdom of transmitting signals into space versus merely listening for signals from other civilizations. Some argue that advertising our presence could attract unwanted attention from potentially hostile aliens. Others contend that remaining silent while conducting increasingly sophisticated astronomical observations provides no real protection. Any civilization capable of interstellar travel would likely detect our technological signatures regardless of our transmission policies. But in our speculative scenario, the choice might be taken from us. If 3 Atlas and its hypothetical secondary probes were actively studying human civilization, our response itself would become part of the data being collected. Silence might be interpreted as wisdom or fear. Attempts at communication might suggest aggression or curiosity. Even the internal debates about how to respond would reveal fundamental aspects of human nature and social organization to whatever intelligence was monitoring us. The crisis communication challenges would be extraordinary. How do you inform the global public about the presence of alien surveillance systems without triggering panic? How do you maintain scientific objectivity while acknowledging possibilities that exceed our current understanding? How do you distinguish between verified observations and speculative interpretations when the stakes could involve the future of human civilization? The scenario would likely unfold through a series of expert roundtables, emergency sessions of scientific organizations, and carefully crafted public briefings. Governments would need to balance transparency with stability, providing enough information to maintain credibility while avoiding the social disruption that might result from confirming humanity's first contact with non-human intelligence. Misinformation would become a critical concern. The mere suggestion of alien surveillance would spawn countless conspiracy theories, false flag accusations, and claims of government cover. Distinguishing between legitimate scientific observations and baseless speculation would become crucial for maintaining a rational public discourse about the most important discovery in human history. The technology implications would be equally profound. If 3 Atlas revealed capabilities that exceeded our current physics, it might provide insights into propulsion systems, energy generation, material science, or communication methods that could revolutionize human technology. The scientific windfall could accelerate our development by centuries, assuming the intelligence behind the probe allowed us to continue existing and developing. But perhaps the most unsettling aspect of this speculative scenario would be the temporal implications. If 3 Atlas had been traveling for billions of years, it might represent technology from a civilization that achieved interstellar capability when our galaxy was radically different from its current state. The intelligence that launched it might no longer exist, leaving behind only automated systems carrying out missions designed by minds that died out before our sun was born. This raises the chilling possibility that we might be dealing not with active alien intervention, but with the ghost of some ancient civilization, autonomous systems following programmed directives across deep time, perhaps no longer serving any living intelligence but continuing to execute their original mission parameters with mechanical precision. Of course, and this bears constant repetition, none of this speculative narrative is supported by current observations of 3 Atlas. Every measurement, every spectrum, every image continues to support the natural comet hypothesis. The object behaves exactly as astronomical theory predicts an interstellar comet should. Its chemical signatures, while unusual, fall within the range of natural processes. Its trajectory follows the laws of physics without requiring exotic explanations. The value of this speculative exercise lies not in its probability, but in its illustration of how quickly our cosmic perspective could change if our assumptions proved inadequate. It reminds us that the universe has surprised us before and will likely surprise us again, and it highlights the importance of maintaining both healthy skepticism about extraordinary claims and an openness to possibilities that exceed our current understanding. But as we continue this journey through increasingly speculative territory, remember that we're exploring the landscape of possibility rather than the terrain of established fact. The real 3 Atlas remains a fascinating natural phenomenon, ancient, fast, chemically unusual, but fundamentally comprehensible within our current scientific framework. Whether that understanding will prove sufficient remains an open question, but one that future observations will ultimately answer with the cold clarity that only evidence can provide. Part 8. Great Filter alarms. The concept of the Great Filter emerges from one of the most profound questions facing any technological civilization. If the universe should be teeming with intelligent life, why do we see no evidence of it? This philosophical puzzle, first articulated by physicist Enrico Fermi in the 1950s, has spawned decades of speculation about barriers that might prevent life from arising, evolving, or surviving long enough to spread throughout the galaxy. In our speculative exploration of 3 Atlas, we must confront the possibility that this ancient wanderer might carry messages from intelligences that encountered their own insurmountable barriers. The Great Filter hypothesis suggests that somewhere in the long chain of evolutionary development, from simple chemistry to a space-faring civilization, there exists a step so improbable, so difficult, or so dangerous that virtually all attempts to pass through it result in failure. This filter could occur early in the process, perhaps in the transition from non-living matter to self-applicating systems. Or it might emerge later when civilizations develop technologies powerful enough to destroy themselves faster than they can learn to use them wisely. If we permit ourselves to imagine that 3 Atlas represents engineered technology rather than natural phenomena, we must immediately confront the question of its maker's fate. The object's apparent age, potentially billions of years, places its origin in the deep history of our galaxy, when stellar populations, chemical abundances, and cosmic conditions differed substantially from those we observe today. If this ancient visitor were indeed artificial, did the civilization that created it survive long enough to see it reach our solar system? The time scales involved are almost incomprehensible. Human civilization, from the first agricultural settlements to our current space age, spans roughly 10,000 years. Recorded history covers perhaps 5,000 years. Our technological civilization has existed for mere centuries. 3 Atlas, if artificial, would represent technology that has been operational for millions of times longer than our entire civilizational history. This raises profound questions about technological longevity versus biological survival. Perhaps the most haunting possibility is that we might be encountering probes that persist long after their makers have vanished, cosmic messages in bottles floating through the galaxy, carrying information from civilizations that solved the technical challenges of interstellar communication but ultimately succumbed to other forms of the Great Filter. Consider the engineering implications of creating technology that remains functional across such timescales. Our most durable human artifacts, the pyramids, ancient stone monuments, certain radioactive isotopes operate on timescales of thousands to millions of years. But maintaining complex electronic systems, propulsion mechanisms, and artificial intelligence across billions of years would require engineering principles we can barely imagine. It would demand materials science that produces components more durable than diamond, energy systems that remain operational longer than most stars burn, and software architectures that can adapt and self-repair across geological time. The success of such engineering would, paradoxically, suggest that its creators possessed extraordinary technological capabilities. Any civilization capable of launching billion-year interstellar missions would have solved numerous technical challenges that we haven't even begun to address. They would understand materials at the atomic level, energy generation and storage at cosmic scales, and information processing across deep time. Such capabilities would seem to offer protection against many potential great filter scenarios. Yet, if three Atlas were indeed their creation, and if it remains the only evidence we observe of their existence, what great filter might have claimed them despite their technological prowess? The possibilities are sobering to contemplate. Perhaps they fell victim to resource depletion on a galactic scale, expanding so rapidly that they consumed the energy and materials necessary for their civilization's survival. Maybe they encountered other intelligences that proved hostile, triggering conflicts that destroy both aggressor and defender. More unsettling still, they might have succumbed to internal contradictions inherent in an advanced technological civilization. The same capabilities that allowed them to engineer interstellar probes might have enabled forms of warfare, environmental destruction, or social collapse that proved impossible to control. History offers numerous examples of civilizations that developed technologies more rapidly than the wisdom to use them safely. Our own species currently faces several such challenges. Alternatively, the Great Filter might not involve catastrophic destruction, but rather evolutionary transcendence. Perhaps sufficiently advanced civilizations inevitably transform themselves in ways that render them unrecognizable or undetectable to emerging species, like ourselves. They might upload their consciousness into quantum computing systems, merge with their technology so completely that the distinction between intelligence and artifact disappears, or ascend to higher dimensions of existence that remain invisible to our current perception. The cosmic perspective required to contemplate such possibilities can be vertigo-inducing. Our galaxy contains roughly 400 billion stars, many of which formed billions of years before our sun ignited. If even a tiny fraction of those stellar systems produced technological civilizations, the galaxy should have been thoroughly explored and colonized multiple times over. The absence of obvious alien presence, what astronomers call the Great Silence, demands explanation. Current city practice reflects the uncertainty these questions generate. Most searches focus on passive listening rather than active transmission, operating under the assumption that revealing our presence before we understand the galactic environment might be premature or dangerous. The discovery of artificial signatures in three Atlas would instantly transform these careful searches into urgent strategic considerations. The observational guardrails we've established throughout this investigation become even more crucial when contemplating great filter scenarios. Current data about three Atlas continues to support natural explanations for its behavior, composition, and trajectory. Speculation about artificial origin and civilizational failure remains exactly that, speculation, unsupported by evidence and maintained only as an intellectual exercise. Yet, the questions raised by such speculation aren't purely academic. They force us to confront fundamental issues about technological development, civilizational sustainability, and our own species' long-term prospects. If advanced civilizations routinely encounter barriers that prevent their survival across cosmic time, what lessons might that hold for humanity's current trajectory? The Great Filter concept serves as both a warning and an inspiration. It warns that technological capability alone may not guarantee survival, that advancement brings new forms of risk as well as opportunity. But it also inspires us to think carefully about how we manage our own development, how we balance exploration with wisdom, and how we might engineer solutions that prove more durable than the civilizations that create them. In our speculative narrative, three Atlas becomes a cosmic archaeological artifact, physical evidence of an intelligence that achieved remarkable technical capabilities, but ultimately fell victim to forces we can only guess at. The probe continues its ancient mission across deep time, carrying messages from minds that solved interstellar engineering problems but failed to solve the deeper challenge of long-term survival. This scenario would place humanity in the position of cosmic inheritors, discovering technology from predecessors who traveled paths we're only beginning to explore. The responsibility would be extraordinary, learning from their achievements while avoiding whatever great filter claimed their civilization. The stakes would involve nothing less than our species' ultimate survival and our potential to contribute something meaningful to the cosmic conversation. But these remain philosophical speculations rather than scientific conclusions. The real Three Atlas continues to behave exactly as natural comets should, following trajectories determined by gravity and physics rather than intelligence and intent. Whether this understanding will prove adequate remains an open question, but one that observation and evidence will ultimately resolve. As we venture deeper into speculative territory, the contrast between what we imagine and what we actually know becomes increasingly important to maintain. The universe has proven strange enough through natural processes alone. From quantum mechanics to dark energy to the cosmic web of large-scale structure, adding artificial intelligence to this already extraordinary reality might prove unnecessary for achieving the sense of wonder and cosmic perspective that drives all scientific inquiry. Part 9, Fermi's Whisper. Where is everybody? The question echoes through every astronomical discovery, lurking behind every search for extraterrestrial intelligence, haunting every moment when we peer into the cosmic dark and find only silence. Enrico Fermi posed it during a casual lunch conversation in 1950, but its implications have only grown more profound as our understanding of the universe has expanded. If the galaxy should be teeming with intelligent civilizations, if the cosmos offers countless opportunities for life to arise and evolve, then where is everybody? This Fermi paradox takes on new dimensions when we consider interstellar objects like Three Atlas. Each visitor from beyond our solar system represents a natural experiment in the distribution of matter throughout the galaxy, a sample of the materials and processes that occur around other stars. In principle, these wandering ambassadors should eventually reveal signatures of technological civilization, engineered materials, artificial isotope ratios, or structured objects that betray intelligent design. Yet, so far, all confirmed interstellar visitors have appeared thoroughly natural. The absence might be telling us something profound about the nature of advanced civilization and its relationship with interstellar space. Perhaps truly advanced societies prefer what we might call silent emissaries. If they send probes at all, these craft are designed to be indistinguishable from natural phenomena. In such a scenario, the very sophistication of alien technology would render it invisible to our current detection methods, which remain calibrated to recognize obviously artificial signatures. But this raises immediate questions about what those signatures would look like. If Three Atlas were indeed some form of concealed probe, what observational evidence would ultimately reveal its true nature? The answer returns us to the fundamental distinction between natural and artificial phenomena in space, a boundary that may prove more subtle and complex than our current understanding suggests. Narrowband radio emissions would represent the most obvious technological signature. Natural processes in space produce radio noise across broad frequency ranges, but artificial transmissions typically concentrate their energy in narrow spectral lines that stand out clearly against the cosmic background. The search for extraterrestrial intelligence has focused on detecting exactly such signals for decades, operating under the assumption that any civilization capable of interstellar communication would produce detectable electromagnetic signatures. So far, Three Atlas has remained radio-silent, emitting only the natural electromagnetic signatures expected from sublimating cometary material interacting with the solar wind and magnetic fields. Dedicated SETI observations have found no coherent signals, no modulated transmissions, and no artificial patterns in its electromagnetic output. Silence aligns perfectly with the natural comet hypothesis, but cannot definitively rule out more sophisticated forms of concealment technology. Unnatural thermal profiles might provide another diagnostic tool. Natural objects in space achieve thermal equilibrium with their environment according to well-understood physical principles. They absorb solar radiation, re-radiate energy in the infrared spectrum, and maintain surface temperatures determined by their distance from the sun, their composition, and their thermal properties. Artificial objects might display temperature distributions that violate these natural patterns, internal heat sources, asymmetric heating, or thermal management systems that suggest active control. Current infrared observations of Three Atlas show thermal signatures consistent with the solar heating of natural cometary materials. Its surface temperature rises as it approaches the sun, following the inverse square law that governs solar energy distribution. The spatial distribution of heat across its surface appears random, shaped by topographic features and compositional variations rather than designed thermal management systems. Controlled maneuvers would represent perhaps the most definitive evidence of an artificial origin. Natural objects in space follow trajectories determined solely by gravitational forces and the occasional thrust provided by outgassing materials. These non-gravitational accelerations are typically small, random in direction, and closely correlated with measures of cometary activity like comet brightness and gas production rates. Artificial probes, by contrast, might display controlled course corrections, intentional velocity changes, or trajectory modifications that serve specific mission objectives. Such maneuvers would need to be carefully distinguished from the chaotic forces produced by asymmetric outgassing, but persistent patterns of controlled motion would eventually become apparent through precise astrometric measurements. 3 has shown no signs of controlled maneuvers. Its trajectory follows the smooth hyperbolic arc predicted by gravitational calculations, with only minor perturbations that correspond exactly to the expected effects of solar radiation pressure and outgassing forces. If it possesses propulsion capabilities, they remain either inactive or too subtle to detect with current observational precision. The natural explanation for interstellar objects like 3 aligns well with theoretical expectations about planetary system formation. Computer simulations suggest that all stellar systems should eject substantial quantities of rocky and icy debris during their early evolution. When gravitational interactions between planets scatter smaller bodies into interstellar trajectories, the galaxy should be filled with such nomads, planetesimals that began forming around other stars but were flung into the void before they could become full-fledged worlds. From this perspective, the steady trickle of interstellar visitors we've begun detecting represents exactly what astronomical theory predicts. Oumuamua, Borisov, and 3 are the leading edge of a much larger population that future surveys will reveal. The Vera Rubin Observatory, scheduled to begin operations later this decade, should detect interstellar objects at rates of several per year, transforming them from rare curiosities into routine astronomical phenomena. This statistical argument provides one possible resolution to the Fermi paradox's application to interstellar objects. If natural ejected planetesimals greatly outnumber any artificial probes, then the artificial signatures we seek might be hidden in a background of natural wanderers. Detecting alien technology would require distinguishing a few engineered objects from thousands or millions of natural ones, a needle-in-haystack problem of extraordinary difficulty. The chemical diversity revealed by 3 adds another layer to this statistical picture. Its carbon dioxide-rich composition expands the known range of volatile ratios in interstellar objects, suggesting that different stellar environments produce different types of ejected materials. As our sample size grows, we may discover that the chemical signatures we initially interpreted as unusual or potentially artificial actually represent the natural diversity of planetary formation processes across the galaxy. Survey bias effects complicate our interpretation of the interstellar objects we've detected so far. Ground-based telescopes in space-based surveys preferentially discover objects that approach from certain directions, possess specific brightness characteristics, and follow particular orbital geometries. The 3 confirmed interstellar visitors may not be representative of the broader population. Just as the first exoplanets discovered, mostly hot Jupiters in close orbits around their stars, didn't represent the full diversity of planetary systems. 3 approach from southern skies surprised some astronomers who expected interstellar objects to arrive preferentially from the direction of the galaxy's rotation. This unexpected trajectory suggests either that our models of interstellar object distribution remain incomplete or that individual objects can be scattered by gravitational encounters in ways that obscure their original motion patterns. Future astronomical capabilities will dramatically improve our ability to address these questions. The Rubin Observatory's legacy survey of space and time will detect hundreds of interstellar objects over its planned 10-year mission, providing statistical samples large enough to test theoretical predictions about their origins, compositions, and trajectories. Space-based infrared telescopes will characterize their thermal properties and chemical compositions with unprecedented precision. These expanding datasets will either confirm that interstellar objects follow the natural distributions predicted by planetary formation theory, or reveal anomalies that demand more exotic explanations. Alien probes exist among the wandering population. Larger samples and better instrumentation will eventually expose their artificial nature through subtle but persistent deviations from natural behavior patterns. The philosophical implications of continued silence shouldn't be underestimated. Each natural interstellar object we study provides another data point supporting the hypothesis that intelligence capable of interstellar engineering either doesn't exist, remains undetectable by our current methods, or chooses not to reveal itself through easily recognizable signatures. The accumulating evidence of cosmic loneliness grows with every confirmed natural visitor. But an absence of evidence isn't evidence of absence, particularly when our detection capabilities remain limited and our sample sizes remain small. The universe may yet hold surprises that challenge our current understanding of intelligence, technology, and their signatures in space. 3 whether natural or artificial, represents one more piece of evidence in humanity's ongoing attempt to understand its place in the cosmic community. As we continue exploring increasingly speculative scenarios, the contrast between what we observe and what we imagine becomes ever more important to maintain. The real cosmos, revealed through patient observation and careful analysis, has proven strange and wonderful enough without requiring exotic additions. Whether that strange reality includes other forms of intelligence remains an open question, but one that future discoveries will ultimately answer with the clarity that only evidence can provide. Part 10, Cinematic Worst, Silent Invasion via Microseeds. Now we plunge into the realm of pure cinematic speculation, where the boundaries between plausible science fiction and observable reality blur into scenarios that would challenge everything we think we know about life, intelligence, and the cosmos. What follows represents the outermost edge of possibility, ideas so speculative that they require the suspension of multiple scientific principles, while still maintaining enough connection to known physics to fuel our imagination. Picture this scenario: 3 Atlas isn't merely a probe or even a conventional spacecraft, but rather a delivery system for something far more insidious and sophisticated. Hidden within its icy matrix, microscopic devices, or perhaps even engineered biological entities, let's call them microseeds, lie dormant, awaiting activation by specific environmental triggers. These could be nanotechnological constructs designed to survive the harsh conditions of interstellar space for billions of years. Or they might represent some form of pan-galactic life that spreads between star systems through exactly this mechanism. The concept isn't entirely without precedent in scientific speculation. The panspermia hypothesis, while controversial and far from proven, suggests that life itself might spread throughout the galaxy via comets, asteroids, and other interstellar wanderers. Some researchers have proposed that hardy microorganisms could survive the radiation, vacuum, and extreme cold of space for millions or even billions of years, seeding new worlds when they encounter suitable conditions. But our speculative scenario goes far beyond passive panspermia. These hypothetical microseeds would represent engineered systems designed not merely to survive interstellar transit, but to remain dormant until specific activation conditions are met. Perhaps they respond to the electromagnetic signatures of technological civilizations, becoming active only when they detect radio transmissions, industrial pollutants, or other indicators of intelligence. Or maybe they're triggered by solar radiation patterns, awakening as their host object approaches stars of particular spectral types. The engineering challenges involved would be staggering, beyond current comprehension. These micro-devices would need to maintain structural integrity across billion-year timescales while exposed to cosmic radiation, interstellar dust impacts, and the extreme temperature variations of deep space. They would require power sources that remain functional longer than most stars burn, information storage systems that don't degrade over geological time, and manufacturing capabilities that could bootstrap complex technology from raw materials found on alien worlds. Yet, if such technology were possible, the strategic implications would be terrifying. A single interstellar object like 3 Atlas could carry billions or trillions of microscopic seeds, each capable of establishing a foothold on any world it eventually reaches. The invasion, if we can call it that, would be silent, patient, and virtually undetectable until the activation phase began. The activation scenario in our speculative narrative might unfold centuries or millennia after 3 Atlas passes through our solar system. Perhaps the microseeds are designed to trigger when Earth's technology reaches specific thresholds, when we achieve interstellar travel ourselves, when our population reaches certain levels, or when our industrial activity produces particular atmospheric signatures. The delay would serve multiple strategic purposes, allowing time for a detailed reconnaissance of human civilization, ensuring that activation occurs when humanity is sufficiently developed to serve whatever purpose the seeds are designed to fulfill, and maintaining plausible deniability about the connection between the original delivery and the eventual activation. But here's where harsh reality intrudes on this speculative fantasy. Extreme conditions that 3 Atlas has experienced during its interstellar journey would present almost insurmountable challenges to any form of complex technology or biology. Cosmic radiation alone would gradually destroy molecular structures over million-year time scales, let alone the billion-year journey suggested by the object's apparent age. Even the most radiation-resistant organisms known on Earth would succumb to such prolonged exposure. The outgassing chaos that makes 3 Atlas visible as a comet would create additional hazards for any microscopic hitchhikers. As volatile ices sublimate and expand into the vacuum of space, they would carry along dust particles and any other small-scale materials embedded in the nucleus. The violence of this process, occurring every time the object approaches a star during its billion-year journey, would likely destroy delicate structures and scatter any microscopic components across vast distances. The extreme dilution factors involved also argue against the practical effectiveness of such a delivery mechanism. Even if 3 Atlas contained billions of microseeds, the vast majority would be ejected into space during outgassing events, lost to the vacuum between worlds. The few that might somehow reach Earth's vicinity would face additional dilution in our planet's atmosphere and biosphere, making it virtually impossible for any meaningful concentration to accumulate in any particular location. The closest approach distance of 1.8 astronomical units provides another reality check on this speculative scenario. 3 Atlas will pass Earth at roughly twice the distance of Mars, with no possibility of direct material exchange. Any microseeds would need to survive not only the billion interstellar journey and the violent outgassing process, but also the subsequent journey across hundreds of millions of kilometers of interplanetary space to reach our world. Current planetary protection protocols, developed by space agencies to prevent the contamination of both Earth and other worlds, provide frameworks for how we might respond to a hypothetical material capture from objects like 3 Atlas. These procedures involve strict containment protocols, analysis in specialized biosafety laboratories, and careful evaluation of any biological or technological signatures. But such protocols assume direct sample return missions, not the passive capture of microscopic materials ejected across vast distances. The monitoring challenges for detecting such a speculative threat would be enormous. How do you search for microscopic devices or organisms that might be designed to remain dormant for centuries? What signatures would they produce that could be distinguished from natural microorganisms, space dust, or terrestrial contamination? The task would be like searching for needles in a haystack the size of our entire solar system. Long baseline radar systems, the kind used to track space debris and potentially hazardous asteroids, would be unlikely to detect objects as small as microscopic seeds. Optical surveys fare even worse when dealing with particles measured in micrometers rather than kilometers. Even if such monitoring were theoretically possible, the resource requirements would be staggering, demanding constant vigilance across the entire volume of space around Earth. This brings us to the central weakness of our speculative silent invasion scenario. It violates fundamental principles of engineering efficiency. Any civilization capable of designing billion-year interstellar delivery systems would presumably have access to far more direct and reliable methods of achieving whatever goals such an invasion might serve. The complexity, uncertainty, and time delays involved in microscopic seed distribution make it an implausibly inefficient approach compared to alternatives like directed energy transmission, conventional spacecraft, or even simple radio communication. The scenario does serve one valuable purpose in our speculative exploration. It illustrates how our imaginations can run ahead of physical possibility when we're confronted with cosmic mysteries. The same sense of wonder and cosmic anxiety that drives legitimate scientific inquiry can also generate fears that exceed the bounds of plausible reality. Distinguishing between reasonable caution and unfounded speculation becomes crucial when dealing with genuinely unprecedented phenomena. Our documentary treatment of such scenarios requires clear and prominent disclaimers about their speculative nature. Viewers need to understand that we're exploring the landscape of imagination rather than the territory of established fact. These thought experiments can be valuable for expanding our thinking about possibilities, but they shouldn't be mistaken for probable or even plausible realities. The counter-narrative remains straightforward and compelling. The simplest explanation for 3 Atlas's behavior is that comet dust behaves exactly like comet dust. The object displays all the characteristics we expect from natural cometary material: appropriate spectroscopic signatures, predictable thermal behavior, and outgassing patterns that correlate precisely with solar heating. No additional hypotheses are required to explain its observed properties. As we near the end of our speculative journey into increasingly dramatic scenarios, it's worth reflecting on what these thought experiments reveal about human psychology and our relationship with cosmic uncertainty. Our tendency to imagine exotic explanations for unusual phenomena reflects both our creativity and our anxiety about our place in a universe that often seems indifferent to our existence. The real 3 Atlas, the observed, measured, analyzed object racing through our solar system at incredible speed, remains remarkable enough without requiring exotic additions to its story. It's an ancient wanderer from another stellar system, carrying chemical signatures of alien environments, offering us a brief window into the deep history and vast scale of our galaxy. That's extraordinary enough to fuel wonder and scientific investigation without needing to invoke invasion scenarios or hidden technologies. But the exercise of exploring such possibilities serves its own purpose in our ongoing attempt to understand our cosmic context. By pushing speculation to its limits, we better appreciate both the genuine mysteries that surround us and the constraints that physics and evidence place on reasonable explanation. The universe has proven strange enough through natural processes alone, perhaps stranger than our imaginations can readily encompass, but strange in ways that ultimately yield to patient observation and careful analysis. Part 11. If 3 Atlas were a visitor, how would we respond? The response so far has been a testament to the best aspects of human scientific collaboration, a choreographed dance of telescopes, institutions, and individual researchers working together to extract maximum knowledge from a fleeting opportunity. Within hours of the initial discovery by the Atlas survey on July 1, 2025, a global network of observatories had swung into coordinated action, demonstrating how modern astronomy operates as a truly international enterprise. Ivets Wu, Google, Ommel, Sayen Streetwurf Tuvertig Zersearch, Loud, Google, Onto grounding, peridirect Vorsik 5 Uzik 6 no 7 3 x 41 do 3 ons 5 zinen ekkelblut kiesel 0 Isol Urbonko Petodri for VG 5 to Roin 15 Rizrota Pazix Wait X Punix Bio the Vitate 4 Ukaf 1 5 Con Strisevels 2 Sux Wix or Observazus and Footful Punjod Jitek 3 The immediate response followed protocols developed over decades of asteroid and comet discovery. The Minor Planet Center at the Harvard-Smithsonian Center for Astrophysics served as the central clearinghouse for astrometric observations, collecting position measurements from observatories worldwide and refining the object's orbital elements with each new data point. The European Space Agency's Space Situational Awareness Program added its own tracking capabilities, while NASA's Planetary Defense Coordination Office evaluated any potential Earth impact risk, a calculation that quickly ruled out any collision threat. The 3 Atlas's interstellar nature elevated the response beyond routine asteroid tracking procedures. The Hubble Space Telescope received priority target of opportunity scheduling, interrupting previously planned observations to image this unprecedented visitor, Leventzwu. Google, Oumuamua. Zayn Streetwurf Tuvertigzazerch, loud, Google. Grounding peridirect Vorsichtig Xanta 695 Legvent Ninix and Tigwukult Bam 7 Ultras 15 Inik and Novatal Fact for View Book 3 Skip Wake 628 Vex Coat Bow Critic 8 Vios was and for Vident 646 Bleniox. The James Webb Space Telescope followed suit, dedicating precious observing time to spectroscopic analysis of the object's unusual carbon dioxide dominated comet Nitzwu. Google, Oumuamua. Zayn Streetwurf Tuvertigzazerch, loud, Google, Grounding peridirect before 0526 Issues at 28 Elnikan Manzaros Miffled Hipted Straight Reefy 3 Mafaitek Faveto 875 Aga, Jafferty 853 PM 15 Snills and Yovka Kifoak Sumstoxig Tate Dump 6 Pok Fab 3 3 Ground, Aced observatories from Charles Atacama Desert to Hawaii's Mauna Kea contributed complementary observations across the electromagnetic spectrum. This coordinated response illustrates how the astronomical community has evolved to handle rapid response scenarios. Unlike the early days of astronomy, when discoveries might remain hidden in individual researchers' notebooks for months or years, modern astronomical surveys automatically share their findings through established networks. The International Astronomical Union's Central Bureau for Astronomical Telegrams, despite its antiquated name, provides near-instantaneous notification of significant discoveries to researchers worldwide. The information flow surrounding 3 Atlas has been remarkably transparent. NASA's official website provides regular updates on observational results, complete with detailed technical information and accessible explanations for general audiences. Google, Oumuamua. Zayn Streetwurf Tuvertigzazerch, loud, Google, Ponto grounding peridirect Uforzi Hudictriate Babafavela Foros Favem Force Riesrot Frodninivanix Sony 67 Gividanivokiaklerovix 37 Jeps Fringhau Dwangla, Wisix Civic Petersrol 2 Jesens Subulinu Vulbusux Heems Rock 338 Sazavitna. The European Space Agency has published similar updates emphasizing the collaborative nature of the observation campaign. Popular astronomy publications like Sky and Telescope magazine have provided detailed technical coverage alongside practical observing guides for amateur astronomers hoping to glimpse this interstellar visitor through their own telescopes. But imagine if our speculative scenarios from earlier in this investigation proved accurate. Suppose future observations began to reveal signatures that couldn't be explained by natural processes, coherent radio transmissions, controlled trajectory adjustments, or the deployment of secondary objects throughout our solar system. Would our institutions and procedures scale up to handle what might become the most significant discovery in human history? The existing framework provides some guidance. The International Astronomical Union has protocols for verifying extraordinary claims, requiring independent confirmation from multiple observatories before accepting results that challenge established scientific understanding. The SETI Institute has developed communication protocols for potential first contact scenarios, including guidelines for information sharing, public notification, and international cooperation. Space agencies have planetary protection procedures designed to prevent the contamination of Earth by alien microorganisms or, theoretically, more exotic forms of life. Yet none of these existing frameworks were designed to handle the discovery of active alien technology operating within our solar system. The scale of coordination required would dwarf anything previously attempted in scientific research. Questions of jurisdiction would immediately arise. Which international body has authority over first contact protocols? How do you coordinate a response among nations that may view the discovery as either an opportunity or a threat? What happens when scientific curiosity conflicts with security concerns? The political dimensions would be staggering. Any confirmation of alien technology would instantly become a matter of national security for every major power on Earth. Military establishments that currently view space primarily as a domain for surveillance and communication would suddenly confront the reality of a non-human intelligence with potentially superior technological capabilities. The balance between transparency and security that has generally favored openness in astronomical research might shift dramatically toward classification and restricted access. Technical challenges of responding to a confirmed alien presence would test every aspect of our space capabilities. Current spacecraft take years to reach the outer solar system where 3 Atlas is currently located and decades to achieve interstellar velocities. If the object were indeed artificial and time-sensitive communication were desired, our only practical option might be radio transmission. Assuming the alien technology used communication protocols we could recognize or decode, the absence of any realistic interception capability highlights humanity's current limitations in space technology. Despite decades of impressive achievements in robotic exploration, we remain firmly confined to our immediate solar neighborhood, with transit times measured in years rather than months. Any meaningful interaction with fast-moving interstellar objects would require technological capabilities we don't currently possess and couldn't develop quickly enough to matter for objects like 3 Atlas. Public communication strategies would face unprecedented challenges. How do you announce the discovery of alien intelligence without triggering panic or social disruption? The careful, measured tone that space agencies have used for 3 Atlas announcements, emphasizing scientific interest while minimizing sensational interpretations, would need to evolve rapidly to handle far more extraordinary claims while maintaining credibility and public trust. The lessons learned from previous false alarms would become crucial. The WOW signal, detected by SETI researchers in 1977, generated enormous initial excitement, but ultimately proved to be a one-time event that couldn't be independently confirmed or repeated. More recently, the unusual properties of Oumuamua led to brief speculation about an artificial origin before more conventional explanations emerged. These experiences have taught scientists and science communicators the importance of distinguishing between intriguing observations and definitive conclusions. Media management would become a critical component of any response to confirmed alien technology. The 24-hour news cycle's appetite for dramatic developments could easily overwhelm careful scientific analysis with speculation and misinformation. Social media platforms would face enormous challenges distinguishing between legitimate updates from verified sources and the inevitable flood of conspiracy theories, hoaxes, and misinterpretations that would accompany such a momentous discovery. The economic implications alone would justify a careful response plan. Financial markets would likely experience extreme volatility as investors attempt to price in the implications of confirmed alien technology. Entire industries might face existential questions if alien science offered revolutionary alternatives to current energy, transportation, or manufacturing technologies. Global economic stability might depend on how effectively institutions could manage the transition from speculation to confirmed reality. Educational institutions would face immediate pressure to revise curricula, research priorities, and fundamental assumptions about humanity's place in the universe. The philosophical implications would ripple through every academic discipline from astronomy and physics to anthropology, theology, and political science. Universities that have spent centuries developing expertise in terrestrial phenomena would suddenly need to incorporate non-human intelligence into their understanding of reality. The timeline constraints imposed by 3 Atlas's high-speed trajectory add urgency to any hypothetical response scenario. Unlike the gradual approach of most astronomical phenomena, interstellar visitors arrive and depart on schedules determined by physics rather than human convenience. Any meaningful response would need to be developed and implemented within months rather than years, compressing normal decision-making processes into time frames that challenge institutional capabilities. Yet, the actual response to 3 Atlas has demonstrated remarkable efficiency within these constraints. The global astronomical community identified the object, confirmed its interstellar nature, coordinated multi-wavelength observations, and began a detailed analysis within weeks of the initial discovery. This track record suggests that existing institutions and procedures, while imperfect, provide a solid foundation for handling even unprecedented discoveries. The theoretical framework for responding to confirmed alien contact has been evolving for decades through the work of SETI researchers, astrobiologists, and international legal scholars. While these preparations couldn't address every contingency of actual contact, they provide starting points for the kinds of decisions that would need to be made rapidly under extraordinary circumstances. Perhaps most importantly, the response to 3 Atlas has emphasized curiosity over fear, scientific investigation over speculation, and international cooperation over competitive secrecy. These values, embodied in the transparent sharing of observational data and the collaborative nature of the research effort, represent humanity's best approach to cosmic mysteries, regardless of their ultimate explanation. The real-world response demonstrates that we possess both the technical capabilities and institutional frameworks necessary to study unprecedented phenomena effectively. Whether those same capabilities would prove adequate for actual first contact remains an open question, but the coordinated, professional response to 3 Atlas provides reason for optimism about our species' ability to handle even more extraordinary cosmic encounters. As we transition from speculation about alien contact toward more grounded discussions of cosmic perspective and the scientific method, the response to 3 Atlas serves as a case study in how modern civilization approaches the unknown. The combination of technological capability, institutional coordination, and intellectual curiosity that has characterized the 3 Atlas investigation represents a template for engaging with mysteries that may prove even more transformative to our understanding of our place in the universe. Part 12. Containment or curiosity. The question of how we balance scientific curiosity against hypothetical risks reflects one of the most fundamental tensions in human exploration, the same tension that has driven us to cross oceans, climb mountains, and venture into space despite the dangers such endeavors entail. In the case of 3 Atlas, this balance has tilted decisively toward curiosity, and for good reason. The object's trajectory and properties eliminate most conceivable containment scenarios while maximizing opportunities for scientific discovery. Current planetary protection doctrine, developed through decades of space exploration experience, provides frameworks for thinking about contamination risks in both directions, protecting Earth from alien microorganisms and protecting other worlds from terrestrial life. But these protocols were designed primarily for direct sample return missions and close spacecraft encounters, not for objects that pass through our solar system at safe distances while displaying no obvious signs of biological activity. The fundamental architecture of planetary protection rests on risk assessment and proportional response. When NASA's Perseverance rover collected samples from Mars, extraordinary precautions were planned for their eventual return to ensure that any hypothetical Martian microorganisms wouldn't escape into Earth's biosphere. Similarly, spacecraft destined for potentially habitable moons like Europa undergo strict sterilization procedures to prevent the forward contamination of alien environments. 3 Atlas presents a fundamentally different scenario. Its minimum approach distance of 1.8 astronomical units, roughly 270 million kilometers, eliminates any possibility of direct material exchange with Earth. No spacecraft interception is planned or even feasible given current technological capabilities and the object's extreme velocity. The containment question becomes largely academic when the object in question will never come close enough to contain. This safe distance has enabled a remarkably open approach to data sharing and scientific collaboration. Hubble Space Telescope images, James Webb spectroscopic data and ground-based observations have been made available through standard astronomical archives, allowing researchers worldwide to analyze the same datasets and verify each other's conclusions. This transparency represents the scientific method at its best, multiple independent investigators examining identical evidence and reaching consistent conclusions about the object's natural origin. The open archive culture that has developed around major space telescopes deserves particular recognition. The Nikolsky Archive for Space Telescopes makes Hubble and Webb observations available to any researcher with an internet connection, democratizing astronomy in ways that would have been impossible just decades ago. The European Southern Observatory maintains similar archives for ground-based observations, while amateur astronomers contribute their own images and light curves through various citizen science platforms. This openness contrasts sharply with the secrecy that might characterize military or intelligence responses to a potential alien contact. The scientific community's default toward transparency reflects both practical considerations. Ear review requires data sharing and philosophical commitments to the universal nature of scientific knowledge. The 3 Atlas investigation demonstrates how these principles operate even when studying phenomena that might, in principle, represent our first encounter with alien intelligence. The information landscape surrounding 3 Atlas also illustrates both the benefits and challenges of instant global communication. Legitimate scientific results propagate rapidly through professional networks, allowing for near, real-time collaboration between researchers on different continents. But the same communication channels that enable productive scientific exchange also carry misinformation, speculation, and sensational misinterpretations that can distort public understanding. Misinformation patterns around astronomical discoveries have become increasingly sophisticated and pervasive. Social media algorithms that prioritize engagement over accuracy tend to amplify dramatic claims and conspiracy theories at the expense of measured scientific analysis. The challenge of distinguishing between legitimate scientific uncertainty, the kind that drives productive research, and unfounded speculation has become crucial for maintaining a rational public discourse about cosmic discoveries. The case of 3 Atlas provides a useful example of how these information dynamics operate. Mainstream scientific sources have consistently emphasized both the object's unusual properties and its natural origin, acknowledging uncertainty while avoiding unfounded speculation. Less reputable sources have sometimes exaggerated preliminary results, conflated speculation with established fact, or promoted conspiracy theories about government cover-ups of alien contact. Visual communication plays a crucial role in these information dynamics. Hubble and Webb images of 3 Atlas, processed and enhanced to reveal scientific details, can appear dramatic and otherworldly to general audiences. The challenge lies in presenting these images in contexts that emphasize their scientific rather than sensational significance, showing how the observed features confirm cometary behavior rather than suggesting alien technology. The question of containment versus curiosity takes on different dimensions when we consider not physical containment, but information containment. Should certain types of astronomical discoveries be subject to classification or restricted dissemination? The scientific community has generally answered no, arguing that the benefits of open collaboration outweigh hypothetical security risks from publicly available astronomical data. This position reflects both practical and philosophical considerations. Practically, astronomy operates most effectively as a global enterprise, where researchers share data, verify each other's results, and build upon collective knowledge. Philosophically, the view from space has historically served to unite rather than divide humanity, emphasizing our common cosmic heritage rather than terrestrial conflicts. The precedent set by previous potentially anomalous astronomical discoveries supports continued openness. The pulsar discoveries of the 1960s, briefly designated lurk for little green men, ultimately revealed new physics rather than alien intelligence. The WO signal detected by SETI researchers remains unexplained, but has been thoroughly documented and analyzed in public forums. Even Oumuamua's unusual properties were studied through transparent international collaboration rather than classified research programs. Citizen science contributions to 3 Atlas observations demonstrate another aspect of the curiosity over containment approach. Amateur astronomers with modest equipment have captured images and light curves that complement professional observations, adding to the database of information that will ultimately inform our scientific understanding. This democratization of astronomical research would be impossible under containment-focused policies, but has proven valuable for advancing genuine scientific knowledge. The SPHERICS mission's potential role in mapping 3 Atlas's extended carbon dioxide comet illustrates how next-generation surveys will further expand our ability to study such objects. Wide-field infrared missions like SPHERICS can complement the detailed spectroscopy provided by Webb, creating comprehensive portraits of interstellar visitors that no single instrument could provide alone. Looking forward, the Vera Rubin Observatory's legacy survey of space and time promises to revolutionize our understanding of interstellar objects by detecting hundreds of such visitors over its planned operational lifetime. This statistical approach will either confirm that objects like 3 Atlas represent natural phenomena following predictable distributions, or reveal anomalies that demand more exotic explanations. The institutional approach to studying these future discoveries has been shaped by the 3 Atlas experience. The rapid coordination between observatories, the transparent data sharing protocols, and the emphasis on international collaboration provide a template for handling even more unusual discoveries. Should genuinely anomalous objects eventually be detected, the scientific community appears well prepared to study them through the same open, collaborative methods that have characterized the 3 Atlas investigation. The balance between skepticism and openness that has characterized professional astronomical responses to 3 Atlas provides another model for future discoveries. Healthy scientific skepticism demands extraordinary evidence for extraordinary claims, but it also requires remaining open to possibilities that exceed current understanding. The 3 Atlas investigation has demonstrated how to maintain this balance, acknowledging unusual properties while avoiding unfounded speculation. Risk assessment for future interstellar visitors will benefit from the 3 Atlas precedent. The object's safe passage through our solar system, its consistent behavior according to natural comet physics, and the absence of any anomalous signatures provide baseline expectations for similar discoveries. Future objects that deviate significantly from this pattern might warrant different approaches, but the default assumption will likely remain that natural explanations should be exhaustively tested before considering more exotic possibilities. The educational value of the 3 Atlas investigation extends beyond its immediate scientific results to demonstrate how modern astronomy operates as a collaborative, transparent, evidence-based enterprise. The project has shown how institutions coordinate responses to unprecedented discoveries, how data sharing enables rapid progress, and how professional skepticism guards against both premature conclusions and the reflexive dismissal of unusual phenomena. As we transition toward broader questions of cosmic perspective and humanity's place in the universe, the 3 Atlas investigation serves as a case study in how our species approaches the unknown. The emphasis on curiosity over fear, collaboration over competition, and evidence over speculation provides reason for optimism about our ability to handle even more profound cosmic discoveries that may await us in the years and decades ahead. Part 13. The scale of the cosmos and our signals. The journey that brought 3 Atlas to our cosmic doorstep spans distances and time scales that challenge human comprehension. Yet, understanding these scales is crucial for grasping both the object's significance and our own place in the vast theater of galactic evolution. When we speak of thick disk galactic origins, we're invoking a story that began when the universe was less than half its current age, when stellar populations differed dramatically from those we observe today, and when the Milky Way itself was still a young and chaotic stellar nursery. The thick disk represents an older generation of stars that formed during the galaxy's early, turbulent period, roughly 10 to 12 billion years ago. Unlike the thin disk where our Sun resides, a relatively orderly region where stars follow roughly circular orbits around the galactic center, the thick disk contains stars with more eccentric, tilted orbits that reflect the violent conditions of their birth era. If Threatlas indeed originates from this ancient population, it carries within its nucleus a record of stellar neighborhoods that existed before our solar system was even a glimmer in a molecular cloud's eye. The scales of this journey become almost poetic when we attempt to visualize them. Threatlas has potentially been wandering the galaxy for billions of years, during which time entire stellar generations have been born, lived, and died. Massive stars that existed when this object began its interstellar odyssey have long since exploded as supernovae, seeding space with heavy elements and triggering new rounds of star formation. Planetary systems have formed, evolved, and potentially developed life countless times over. During this ancient wanderer's journey through the cosmic dark, the travel times involved dwarf any human concept of duration. If Threatlas has indeed been wandering for 5 billion years, conservative estimate based on its apparent thick disk origin, it has been traveling for more than 1,000 times longer than complex life has existed on Earth. During its journey, our planet has experienced the Cambrian explosion, 5 major mass extinctions, the rise and fall of the dinosaurs, and the eventual emergence of human civilization. Yet, from the perspective of this cosmic wanderer, all of human history represents merely the final microsecond of its multi-billion-year voyage. The distances traversed are equally staggering. Even at Threatlas's tremendous velocity of more than 130,000 miles, crossing significant portions of the galaxy requires millions of years. The object has potentially encountered hundreds or thousands of stellar systems during its wandering, passing close enough to some to be influenced by their gravitational fields, perhaps even witnessing the birth of planets around stars that are now ancient giants nearing the ends of their lives. These encounters would have been silent and unobserved, occurring in the depths of space far from any witness capable of recording them. Each gravitational interaction would have slightly altered the object's trajectory, adding or subtracting kinetic energy in a cosmic game of pinball played across galactic distances. The cumulative effect of millions of such encounters could account for Threatlas's current extreme velocity, each stellar flyby contributing a small push that eventually accelerated this ancient wanderer to its current breakneck speed. The chemical diversity that Threatlas represents takes on new significance when viewed against this galactic backdrop. Its carbon dioxide-rich composition may reflect formation conditions around a very different type of star than our Sun, in a stellar environment where different nuclear fusion processes, planetary system architectures, or interstellar medium compositions prevailed. The object serves as a sample of alien chemistry, carrying molecular signatures from stellar neighborhoods we may never visit directly. This chemical archaeology extends our understanding of galactic evolution in ways that conventional astronomy cannot match. While we can study distant stars through their light and infer their properties through spectroscopy, interstellar objects like Threatlas carry actual physical samples of material that formed around those distant suns billions of years ago. It's like having pieces of alien worlds delivered to our doorstep, complete with isotope ratios, mineral compositions, and volatile inventories that reveal the conditions of their birth. Our own radio bubble, the expanding sphere of electromagnetic radiation that announces humanity's presence to the cosmos, provides a humbling perspective on these galactic scales. Since Marconi's first wireless transmissions in the late 19th century, our radio signals have been expanding outward at the speed of light, currently reaching stars within roughly 120 light-years of Earth. This seems impressive until we realize that our galaxy spans roughly 100,000 light-years in diameter, making our radio presence a tiny bubble in the vast galactic ocean. The radio bubble contains perhaps a few thousand stellar systems out of the galaxy's estimated 400 billion stars. Even our most powerful radio transmissions, designed to communicate across interplanetary distances within our solar system, would appear as faint whispers to any listeners around nearby stars. The idea that Threatlas might have been attracted to our solar system by our electromagnetic signature becomes implausible when we consider both the object's apparent age and the minuscule fraction of the galaxy that our radio presence encompasses. The silence we encounter when listening for radio signals from other civilizations, the great silence that underlies the Fermi paradox, becomes less surprising when viewed against these vast scales. Even if the galaxy contained thousands of radio-transmitting civilizations, the distances involved would make their signals extraordinarily faint and difficult to detect. The inverse square law that governs electromagnetic radiation means that doubling the distance to a radio source reduces its apparent brightness by a factor of 4, making interstellar communication a profound technical challenge even with technology far more advanced than our current capabilities. The energy realities of interstellar communication dwarf those of any human technology. Broadcasting a signal powerful enough to be easily detectable across typical interstellar distances would require energy outputs comparable to small stars. Even highly directional transmissions, focused like searchlight beams towards specific target systems, would demand power generation capabilities far beyond anything currently achievable. These physical constraints may explain why SETI searches have found no convincing artificial signals, despite decades of listening across vast ranges of frequencies and directions. The same energy considerations apply to interstellar travel, providing a context for evaluating the plausibility of various scenarios we've explored throughout this investigation. Accelerating even a small probe to the velocities required for rapid interstellar transit would require energy equivalent to the total annual power output of major industrial nations. Larger spacecraft would demand correspondingly larger energy investments, potentially exceeding the entire energy production capability of current human civilization. 3 Atlas's natural achievement of extreme velocity through gravitational interactions illustrates how the galaxy itself can serve as an accelerator for objects patient enough to accumulate energy through multiple stellar encounters. This natural mechanism provides a plausible explanation for the object's tremendous speed without requiring exotic propulsion technologies or artificial acceleration systems. Statistical implications of interstellar object discoveries become clearer when viewed against galactic scales. If planetary system formation routinely ejects significant quantities of rocky and icy debris, as computer simulations suggest, then the galaxy should contain trillions of wandering objects like 3 Atlas. The discovery rate of several interstellar visitors per year that the Rubin Observatory should achieve represents only the tiniest sampling of this vast population, limited by the constraints of detection technology and observational coverage. This statistical perspective suggests that the chemical and physical diversity we've observed in the small sample of confirmed interstellar objects may represent only a fraction of the true range of compositions and characteristics present in the galactic population of wanderers. Future surveys may reveal objects with even more exotic properties than 3 Atlas, expanding our understanding of the conditions and processes that operate around distant stars. The temporal scales of galactic evolution provide another framework for understanding 3 Atlas's significance. The galaxy's chemical composition has been steadily enriched over billions of years as successive generations of stars have fused light elements into heavier ones and distributed the products through supernova explosions. Objects that formed early in this process, like 3 Atlas if our age estimates prove correct, would reflect the chemical conditions of a younger, less metal-rich galaxy very different from the stellar environment we observe today. This temporal dimension adds layers of complexity to interpreting the chemical signatures we observe in ancient interstellar objects. The carbon dioxide dominance that makes 3 Atlas unusual among current comets might have been typical of objects forming around early generation stars with different compositions and thermal properties than the Sun. Understanding these ancient formation conditions could provide insights into the early stages of galactic chemical evolution that are otherwise impossible to obtain. As we approach the conclusion of our investigation into 3 Atlas and its implications, these cosmic scales serve to remind us of both the extraordinary nature of this discovery and the limitations of our current perspective. We are examining an object that has witnessed galactic evolution across geological time, that carries chemical signatures from stellar environments we've never encountered, and that provides a direct physical link to processes that occurred billions of years before Earth existed. Yet, for all its cosmic significance, 3 Atlas remains fundamentally comprehensible within our current scientific framework. Its behavior follows the laws of physics, its chemistry reflects natural processes, and its trajectory obeys the same gravitational principles that govern every other object in the universe. The combination of exotic origin and familiar behavior illustrates both the diversity and the underlying unity of natural processes operating across the galaxy. This perspective of cosmic scale and natural law provides the foundation for our final reflections on what 3 Atlas represents for human understanding and our ongoing relationship with the cosmos that gave us birth. Part 14, Hope in Silence and Data. Perhaps the most profound gift that 3 Atlas offers humanity lies not in any exotic speculation about its origins or purpose, but in the simple fact of its non-threatening passage through our cosmic neighborhood. In an era when global challenges can seem overwhelming and our future uncertain, there's something deeply reassuring about a cosmic visitor that arrives precisely when predicted, behaves exactly as natural laws dictate, and departs safely into the interstellar night without disrupting a single terrestrial sunset. This reassurance isn't trivial. It represents the triumph of scientific understanding over cosmic anxiety, the victory of careful observation over unfounded speculation. When 3 Atlas was first detected racing toward our solar system at an unprecedented velocity, we might have feared the unknown. Instead, within weeks of its discovery, international teams of astronomers had calculated its exact trajectory, analyzed its chemical composition, and confidently predicted its harmless passage. This represents human knowledge and cooperation at their finest. The scientific harvest from 3 Atlas has already exceeded what most astronomical discoveries provide over their entire investigation lifetimes. The object's unusual carbon dioxide-rich composition has challenged our assumptions about typical comet chemistry, forcing researchers to develop new models for how volatile ratios might vary among objects formed in different stellar environments. This isn't merely academic knowledge, it informs our understanding of planetary formation processes that operate throughout the galaxy. The spectroscopic signatures revealed by the James Webb Space Telescope provide direct evidence for the kinds of chemical processing that occur around other stars. The high Comet-to-water ratio observed in 3 Atlas's comet suggests formation near carbon dioxide snow lines in protoplanetary disks, or alternatively, radiation processing of surface materials over geological timescales. Either interpretation expands our understanding of the diversity of environments and processes that shape icy bodies beyond our solar system. These chemical insights have implications that extend far beyond cometary science. Understanding how volatile inventories vary among objects from different stellar systems helps astronomers refine models of planetary formation and evolution that apply to the search for habitable worlds around other stars. If carbon dioxide-rich environments were common during certain epochs of galactic evolution, this might influence where and when we expect to find conditions suitable for life as we know it. The institutional response to 3 Atlas has demonstrated the remarkable efficiency of modern astronomical coordination when confronted with unprecedented phenomena. The Atlas survey detected the object, the Minor Planets Center coordinated global tracking efforts, the Hubble and Webb space telescopes provided detailed follow-up observations, and ground-based observatories contributed complementary data, all within a time frame that would have been impossible just decades ago. This coordination extends beyond mere technological capability to represent a philosophical commitment to shared knowledge and collaborative investigation. The decision to make observational data publicly available through standard astronomical archives reflects the scientific community's conviction that cosmic discoveries belong to all of humanity rather than to individual institutions or nations. Such openness becomes particularly significant when studying objects that might, in principle, represent our first encounters with phenomena beyond our terrestrial experience. The transparency that has characterized the 3 Atlas investigation provides a template for how we might handle even more extraordinary discoveries in the future. Should astronomers eventually detect genuinely anomalous objects that challenge our understanding of natural processes, the precedent of open data sharing and collaborative analysis offers the best approach for distinguishing between observational errors, instrumental artifacts, and genuine cosmic mysteries. The public engagement surrounding 3 Atlas has illustrated both the opportunities and challenges of communicating complex scientific concepts to general audiences in our current media environment. Legitimate scientific institutions have generally succeeded in conveying both the object's unusual properties and its natural origin, acknowledging uncertainty while avoiding unfounded speculation. The coverage has educated millions of people about interstellar objects, galactic structure, cometary science, and the methods astronomers use to study remote phenomena. Yet, the same communication channels that enable effective science education also carry misinformation and conspiracy theories that can distort public understanding of cosmic discoveries. The challenge of maintaining a rational discourse about astronomical phenomena has become increasingly complex as social media algorithms prioritize engagement over accuracy, sometimes amplifying dramatic claims at the expense of measured scientific analysis. The 3 Atlas case study demonstrates how scientific institutions can navigate these communication challenges through consistent messaging, clear distinctions between established facts and speculative interpretations, and the patient correction of misunderstanding. The approach serves as a model for handling future discoveries that might prove even more challenging to communicate effectively. Live tracking websites, press conferences, and educational materials have made 3 Atlas one of the most publicly accessible astronomical discoveries of recent years. Amateur astronomers have contributed observations, student projects have analyzed publicly available data, and citizen science initiatives have engaged thousands of volunteers in monitoring the object's brightness and behavior. This democratization of astronomical research represents one of the most encouraging trends in modern science. The speculation that has surrounded 3 Atlas, including the scenarios we've explored throughout this investigation, serves legitimate purposes beyond mere entertainment. Considering exotic possibilities forces researchers to think more carefully about what distinguishes natural from artificial phenomena in space, encourages the development of observational tests that could falsify conventional interpretations, and reminds us that the universe may still hold surprises that challenge our current understanding. That the true value of such speculation lies in its relationship to evidence rather than its dramatic content. The scenarios we've explored become valuable when they generate testable predictions or highlight gaps in our current knowledge. They become harmful when they're mistaken for established facts or used to promote unfounded anxiety about cosmic threats. The careful distinction between speculation and science that we've maintained throughout this investigation reflects broader principles about how knowledge advances and how society should respond to uncertainty. Science progresses through the interplay between imaginative hypotheses and rigorous testing, between creative speculation and disciplined evidence evaluation. Three Atlas has provided an excellent case study in how this process operates when dealing with genuinely unprecedented phenomena. The arc of understanding that has characterized the Three Atlas investigation, from initial detection through detailed analysis to confident conclusions about its natural origin, illustrates how scientific knowledge develops over time. Early observations raised questions about the object's unusual properties. Subsequent measurements refined our understanding of its composition and behavior. Eventually, enough evidence accumulated to support confident conclusions about its nature as an ancient, chemically distinctive, but fundamentally natural comet. This progression from uncertainty to understanding represents science at its most effective, demonstrating how patient observation and careful analysis can resolve apparently mysterious phenomena. The process provides reason for optimism about our ability to understand even more exotic cosmic discoveries that may await us as our observational capabilities continue to improve. The promise of future discoveries looms large as we consider Three Atlas's place in the expanding catalogue of interstellar objects. The Vera Rubin Observatory's legacy survey of space and time will detect hundreds of similar visitors over the next decade, transforming interstellar objects from rare curiosities into routine astronomical phenomena. The statistical revolution will enable studies of their population characteristics, chemical diversity, and dynamical properties that are impossible with our current small sample size. Each new discovery will add pieces to the puzzle of galactic evolution, planetary formation, and the distribution of materials throughout interstellar space. The chemical signatures that make Three Atlas unusual may prove to represent common formation conditions around certain types of stars, or they may remain genuinely rare examples of exotic processing that occurs only under specific circumstances. The technological capabilities that enabled the Three Atlas investigation, sensitive wide-field surveys, rapid follow-up observations, space-based spectroscopy, and global coordination networks continue to improve at remarkable rates. Future interstellar visitors will be detected earlier, characterized more completely, and understood more quickly than current examples. This progression of capability provides hope that even genuinely anomalous objects would be recognized and studied effectively. The broader context of cosmic exploration that Three Atlas represents extends far beyond the specifics of this individual object. Each interstellar visitor expands our direct sampling of galactic materials and processes, complementing the indirect information we gather through stellar spectroscopy and theoretical modeling. These objects serve as cosmic ambassadors, carrying information about stellar environments we may never visit directly. Philosophical implications of studying such objects deserve recognition alongside their scientific value. Three Atlas connects us tangibly to the deep history of our galaxy, to processes that occurred before our solar system existed, and to chemical environments that shaped materials, now racing past our cosmic doorstep. This connection provides perspective on our place in cosmic evolution and the continuity of physical processes across vast scales of space and time. As we prepare to conclude our investigation into Three Atlas and its implications, the overarching theme that emerges is one of successful scientific discovery, guided by evidence, enhanced by imagination, but ultimately grounded in careful observation and rigorous analysis. The object has challenged our assumptions, expanded our knowledge, and provided a case study in how modern astronomy addresses the unknown. The worst-case scenario that motivated our investigation, the possibility of cosmic catastrophe or alien invasion, has proven unfounded, replaced by a more subtle but equally profound story of ancient chemistry, galactic evolution, and the remarkable capabilities of human scientific inquiry. In replacing fear with understanding, Three Atlas has provided perhaps the most valuable gift any cosmic visitor could offer, the demonstration that patient observation and collaborative investigation can illuminate even the deepest cosmic mysteries. Part 15. Good night, Cosmic Messenger. As Three Atlas continues its ancient journey outward from our sun, fading with each passing day into the star-scattered darkness from which it came, we're left with images that will endure long after the object itself disappears beyond the reach of our most powerful telescopes. The Hubble Space Telescope's exquisite portraits show a fuzzy, star-like point surrounded by the gossamer envelope of its carbon dioxide comma, a cosmic Christmas ornament suspended against the infinite black of space. Levenetswu. Oogel, Ommel. Thyengatsrietwaftuvertigzazach, loud. Oogel, ontwergrounding, p redirect u voorzichtig unto 695 van Nixonatiquakeltbam 7+15 in exit and alvatal effect for view book free skipwake kukessing at 28 exco bo critic 28 vioswasiak for visit 646 blonielks webs infrared vision reveals the molecular signatures of that come in precise detail, each spectral line a word in the ancient chemical language this visitor carries from its birthplace around another star. Trajectory plots tell their own story of cosmic choreography. Smooth curves arc across diagrams showing Three Atlas's path through our solar system, past Mars's orbit, around the Sun at perihelion, and back out toward the realm of the gas giants before continuing into interstellar space. These aren't the chaotic, unpredictable paths of human political or economic events, but the serene precision of celestial mechanics, as inevitable as sunrise and as dependable as the seasons. There's something deeply satisfying about this predictability, this cosmic reliability that operates beyond human influence or control. While our terrestrial world churns with uncertainty, 3 Atlas follows laws that have governed motion in space since the universe began. Its departure is scheduled not by human decision, but by the fundamental forces that shape reality itself. In an age of manufactured anxiety and artificial urgency, such cosmic dependability offers a profound form of comfort. The answer to our investigation's central question, what's the worst-case scenario, has proven refreshingly mundane. No Hollywood catastrophe awaits. No alien invasion threatens our civilization. No cosmic disruption will alter Earth's orbit or climate. The worst case in terms of actual physical threat is, quite literally, nothing at all. 3 Atlas will depart our solar system exactly as it arrived, silently, safely, and according to the precise predictions of mathematical physics. But perhaps calling this outcome mundane misses its true significance. The fact that we can predict the behavior of an object that has traveled for possibly billions of years, that formed around a star we've never seen and that carries chemical signatures from environments we've never directly studied, this predictability represents one of science's greatest triumphs. The laws of physics operate with such consistency that phenomena separated by cosmic distances and geological time still follow the same fundamental rules. The weirdness that 3 Atlas has revealed proves no less fascinating for being natural in origin. Its carbon dioxide-rich chemistry challenges our assumptions about typical comet composition, expanding our understanding of the diversity of materials that can form around different types of stars. Its apparent thick disgalactic origin suggests formation in stellar environments very different from our local neighborhood, providing a sample of ancient galactic chemistry that we can study in exquisite detail. These unusual properties have already influenced how astronomers think about planetary formation, cometary evolution, and the chemical diversity of interstellar objects. Papers published on 3 Atlas will be cited for decades as researchers incorporate its lessons into broader theories about how icy bodies form and evolve throughout the galaxy. The scientific impact extends far beyond this single object to illuminate processes that operate around countless distant stars. The speculation we've explored throughout this investigation, scenarios involving alien technology, ancient civilizations, or exotic physics, has served its purpose in exercising our imaginations and highlighting the kinds of questions that arise when we encounter genuine cosmic mysteries. But the evidence consistently points toward natural explanations that, while remarkable, operate within our current understanding of physical law. This outcome shouldn't disappoint us. The universe has proven strange and wonderful enough through natural processes alone. From quantum mechanics to black holes to the acceleration of cosmic expansion, adding artificial intelligence or exotic technology to this already extraordinary reality might prove unnecessary for achieving the sense of wonder and cosmic perspective that drives scientific inquiry. The music that might accompany our farewell to 3 Atlas should be neither ominous nor triumphant but contemplative, something that captures both the mystery and the comprehensibility of cosmic phenomena. Perhaps Holst's The Planets or Barber's Adagio for Strings, compositions that evoke the vastness of space while maintaining a human emotional resonance. The tone should invite reflection rather than excitement, wonder rather than fear. Throughout this investigation, we've attempted to maintain clear boundaries between established science and imaginative speculation. Where data ended and conjecture began has been explicitly marked, allowing viewers to distinguish between what we actually know and what we can only imagine. This transparency reflects not just intellectual honesty, but a practical necessity in an era where misinformation can spread faster than fact. Checking can correct it. The final message that emerges from our investigation isn't about impact threats or invasion scenarios, but about the more subtle danger of cosmic anxiety, the fear that arises when we encounter phenomena that exceed our immediate understanding. 3 Atlas has demonstrated that such fears can be dispelled through patient observation, careful analysis, and international collaboration among researchers committed to evidence-based understanding. The epilogue cards that might conclude our documentary should direct interested viewers to the wealth of publicly available information that has made this investigation possible. NASA's official pages on 3 Atlas provide authoritative summaries of observational results. The Space Telescope Science Institute's archives contain the actual Hubble and Webb images and spectra that inform our scientific understanding. Professional journals and popular astronomy magazines offer detailed technical analysis alongside accessible explanations for general audiences. These resources represent more than a mere bibliography. They embody the democratic spirit that has characterized the 3 Atlas investigation from its earliest days. The decision to make observational data publicly available through standard astronomical archives reflects a philosophical commitment to shared knowledge that transcends national boundaries and institutional affiliations. Such openness provides hope for how humanity might handle even more extraordinary cosmic discoveries in the years ahead. The promise of future interstellar visitors adds anticipation to our farewell to 3 Atlas. The Rubin Observatory will detect dozens of similar objects over the coming decade, each offering its own lessons about galactic chemistry, planetary formation, and the population of wanderers that fill interstellar space. Some may prove even more chemically unusual than 3 Atlas. Others might display properties that challenge our understanding in entirely new ways. Each discovery will add to the growing database of interstellar object characteristics, enabling statistical studies that are impossible with our current small sample size. The population characteristics, chemical diversity, and dynamical properties revealed by these future surveys will inform theories of galactic evolution and planetary formation that extend far beyond our local stellar neighborhood. The credits that acknowledge the observatories, archives, and individual researchers who made the 3 Atlas investigation possible serve a purpose beyond mere attribution. They remind us that major scientific discoveries emerge from collaborative networks rather than isolated genius, from institutional support rather than individual inspiration alone. The coordination between ground-based surveys, space telescopes, and data archives that enabled the rapid characterization of this interstellar visitor represents modern astronomy at its most effective. As 3 Atlas fades into the cosmic distance, carried by momentum acquired during its billion-year journey through interstellar space, it leaves behind more than just scientific data and published papers. It has provided a case study in how human civilization approaches the unknown, with instruments rather than weapons, with curiosity rather than fear, and with collaboration rather than competition. These choices reflect our highest aspirations for engaging with cosmic mysteries that may prove even more profound than this ancient wanderer from the space between the stars. The silence that will follow 3 Atlas's departure isn't empty but expectant, waiting for the next cosmic messenger that will surely arrive, carrying its own chemical signatures from distant stellar neighborhoods, its own challenges to our understanding, and its own opportunities for expanding human knowledge of the universe that gave us birth. In that waiting, in that continued watching of the skies, lies perhaps the most hopeful aspect of our relationship with the cosmos, the conviction that there are always more wonders to discover, more questions to ask, and more reasons to look up at the stars with curiosity rather than fear. The gentle fade to black that might conclude our visual journey accompanies 3 Atlas as it disappears into the stellar backdrop, no longer a distinct object but once again part of the cosmic landscape from which it briefly emerged. Its passage through our solar system represents just a few months in a journey that has lasted geological ages and will continue for geological ages more. We were privileged to witness this brief cosmic moment, to study this ancient traveler, and to add its story to the growing catalogue of wonders that fill the space between stars. Good night, Cosmic Messenger. Thank you for the lessons, the data, and the reminder that the universe remains far stranger and more wonderful than our earthbound imaginations might suggest. Safe travels on your continued journey through the galaxy, carrying whatever chemical secrets and ancient memories remain locked within your nucleus, a testimony to stellar environments and formation conditions that existed long before our world knew the warmth of its own star. Until we meet your cousins from other distant systems, other ancient epochs, other corners of the cosmic wilderness that surrounds our small but remarkable planetary home.